Okay, so this week we are going to focus on what do we do when we have more than two samples. And we're going to focus on when we have one factor in this first lecture. So maybe that factor is multiple races. And then in the next lecture, we're going to focus on what happens when we have more than one factor. And we're in that particular lecture, we'll go through what happens when we have two factors. All right, so let's get started here on an ANOVA. All right, so what is an ANOVA? An ANOVA stands for Analysis of Variance, and we will get into a little bit of the theory here in a minute of why we are referring to variance in the title. But at the end of the day, it's testing for equality of more than two population means. Again, that's a little bit of fancy stats talk for having more than two samples. All right, so we want to go through our assumptions, and again, we're going to want to make sure that that we have these assumptions met. The first and foremost, and we should be used to this one now, is that the populations are normal. All right, and again, for the time being, I am giving you samples that are coming from normal populations. Again, it's a little tricky testing for normalcy of a sample because samples do not have to be normal to come from normal populations. So next week, when we get into regression and start talking about residuals, we will talk about how we can test those residuals for normality. All right, populations have equal standard deviations or variances, so we have homogeneity of the variances. Again, this we're used to. We had the same assumption with our two-sample t-tests. And the populations are independent, so again, this is going back to something similar to our independent two-sample t-tests, but again, now we have more than two samples. All right, so let's go through something. One question students often have is, well, if we know how to do independent two-sample tests and we have more than two samples, why not just run a bunch of two-sample t-tests? And that's a valid question, but let's talk about what actually goes wrong. So here's a good example for you. Suppose there are 4 different methods, A, B, C, and D, of training recruits to be firefighters. We randomly assign each of the 40 recruits to one of the 4 methods. At the end of the training program, we administer to the 4 groups a common test to measure understanding of firefighting techniques. Is there a difference in the mean test scores among the 4 groups? Okay, so if we wanted to do a bunch of two-sample t-tests, well, how many two-sample t-tests would we need to run if we have 4 groups? All right, so we've got 1, 2, 3, 4, 5, and 6. All right, so we would have to run 6 two-sample t-tests. All right, so suppose we have our standard alpha of 5%. You know at this point that means the probability of us making a type 1 error, which is a wrong decision, is 5%. All right, just playing with the complement probability, the probability that we then do not make a type 1 error would be 1 minus 5% or 95%. So in one two-sample t-test with a 5% alpha, there's a 95% chance we do not make an error. All right, now what is the probability all 6 t-test decisions are correct? Uses multiplication rule from probability, so we multiply 0.95 by itself 6 times, and we get 73.5%. So again, once we run 6 of the tests, we no longer have a 95% chance of not making a type 1 error. Now we have a 73.5% chance of not making a type 1 error. All right, meaning the probability that at least one decision is incorrect would be the complement of that, or 1 minus 73.5%, which gives us a 26.5%. So in other words, if we have these 4 groups and we run our 6 t-tests, even if we are rejecting the null at a 5% alpha for all of the 6 tests, we hand over our results and say, well, there's a 26.5% chance I've made at least one mistake. Not good, right? We've got a problem there. All right, so what happens here when you do these two-way comparisons is you get a buildup of type 1 error, which is very bad. All right, so let's talk a little bit about why we want to run an ANOVA. All right, so we've got this treatment or factor, all right, and this is the term used to identify the different populations being examined, all right. Excel uses the word treatment. So if you downloaded the, what is it called, data analysis tool pack in Excel, and you went to run an ANOVA in Excel, which you can do, Excel uses the word treatment. JASP uses the term fixed factor. All right, but again, this is a categorical variable, all right, so categorical or qualitative, all right, which is giving us more than 2 categories. In the firefighter example, it would be the assigned group A, B, C, or D. All right, so let's get into why it is called an ANOVA in the sense that it is an analysis of variance and we're not saying analysis of means. All right, we want to compare the sample means through their variances, all right? And in other words, do the sample means come from one population or multiple populations with different means, okay? So, well, let's go back for 1 second. Let me make sure you understand that. Do the sample means come from one population or multiple populations with different means? How am I getting from one population just by comparing means? And the answer is, remember that one of the underlying assumptions is we have homogeneity or equality of variances. So that's given. To do this test, we have to assume equality of the variances. In other words, the distributions have the same shape. So if the means are equal, then it's a single population because they're all identical on top of one another. If we have different means, then the populations still have the same shape, but they're shifted apart from one another. All right, and so what we do here, and I should say what the software is doing, is estimating the population variance 2 different ways. We find a ratio of these 2 estimates, and if the ratio is close to 1, then logically the 2 estimates are about the same, and we conclude that the population means are the same. However, if the ratio is quite different from 1, then we conclude the population means are not the same. All right, it's all well and good, but here's the statistical question. What is close to 1, right? What constitutes close to 1, what doesn't? So is 2 close to 1? Is 1.5 close to 1? All right, so we are going to use the F distribution. So far in this class, we've talked about the normal distribution, we have talked about the T distribution, and now we are on the F distribution. The F distribution serves as a referee by indicating when the ratio of the sample variance is too much greater than 1 than to have occurred by chance. All right, so that's where we're going to get our p-value from. In the results in JASP, you will see a p-value next to the F value in the ANOVA table. All right, so again, I think statistically, the best way to learn this course is through examples. You can never do too many examples. Suppose there are 4 different groups. So we're going here back to our firefighter example. We've got our A, B, C, and D groups. At the end of the training program, we give them all a test. All right, is there a difference in the mean test scores among the 4 groups? And now we're going to use alpha as 5%. All right, so let's start by writing our null and alternative. What is this going to look like? And you guys are actually going to really like these, because now where maybe writing the null and alternative was a little bit difficult for 1 and 2 samples, it really gets easier once we have more than 2 samples. All right, so we can finally get rid of the symbols, the mu's. All right, so our null is that all group means are equal. All right, and our alternative is at least one group mean unequal, because it only takes one to be unequal to throw off the equality of all of them, right? Here where I'm saying group is specific to this problem because that's what we are calling A, B, C, and D. We could also say method, but what you want to do is name your factor here, and I think you'll catch on to that more once we get over to the classwork. All right, so we want to find the p-value now, right? So let me go out of here and let's go over to our ANOVA lecture. All right, so we've got our group column, A, B, C, and D, and we've got our test scores. So we go into ANOVA. All right, our dependent variable is the continuous variable. That would be the score. And our fixed factor is the A, B, C, and D, which is the group. All right. And before we really look over here, let's just go through a few of these. We're going to come back to this in a minute. All right. With our group, all right, you will see that, and this will become more obvious in the next lecture video when we do two-way ANOVAs, but you'll see model terms, what actually is being added to this table. In other words, if we remove group, then group goes away. We don't have anything in our ANOVA table. So we want to keep group over there since we only have one model term. Sum of squares, we're going to leave it on the default of type 3. All right. And our assumption checks, we can always check for our variances being equal. So here is the Levine test that we're used to. And we're getting our equality here of variances because remember, non-significant p-value or large p-value means variances are equal. All right, so we can always have that. QQ plot of residuals we'll actually talk about next week when we talk about regression and residuals, but that would be your check for normalcy or normality. All right, let's talk about contrast here. There's really nothing to talk about, just that we are assuming equal variances. All right, post hoc we'll come to next time. Descriptive we'll come to in just a minute. Additional options we can talk about. This is always nice, at least where we're at right now. We can talk about descriptive statistics. And one thing we do want to do is check our estimates of effect size. Remember, we always want to see the size of the effect, okay? So we've got our effect size there. Other than that, that's pretty much all. This is where we are at this point. All right, so we've got our ANOVA table. You see your F statistic of is the ratio of the population variances close to 1. Our F statistic is 12, which is giving us a p-value of less than 0.001. This eta squared, and that's ETA, that's a Greek letter. Eta squared is giving us our effect size, and we'll actually talk about that here in just a little bit. And then our descriptives here for our groups, giving us our sample mean and standard deviation and sample size for each of our 4 groups. All right, let's go back over here for the time being. All right, so again, our responses are in 2 columns. We had our dependent variable and our factor, which was the group, and we found our p-value is less than 0.001. All right, since the p-value is really teeny tiny like that, it's less than 5%, so we reject the null hypothesis. Now, how do we conclude? All right, we are concluding the alternative. All right, so there is enough evidence to conclude we do not say that they are unequal. What we say is that there is enough evidence to conclude at least one of the groups or methods has a significantly different mean test score, okay? Remember, it only takes one to throw off equality, and that's all we get from this global ANOVA test, that at least one of them is significantly different. We don't know if all four of them are different from each other. We don't know if there's only one method different from the other three. All right, and so that leads us always to more questions, right? Which group? Is it all the groups? Is it only one group? Is there one method that works better than everything else? Is there one method that's horrible that we should never use again? We don't know. All right, but let's talk about the breakdown and variation. All right, so the total variation is the sum of the square differences between each observation and the overall mean. So from each of the four groups, right, we've got a variation, a sum of the square difference between that observation and the overall mean of all of them, of all the scores, all right, and that gives us our total variation, all right. Let me go over here and show you where that is. Actually, sorry, we do not get that. The sum of the squares, so if we added the sum of the squares here, this 3708.9 and the 3662.2, if we added those two numbers, that would give us the sum of the squares of everything, all right? This does not tell us much, all right? So what we're really interested in is the sum of the squares of the group and the sum of the squares of the residual. And every time you hear the word residual, I want you to train your brain to fire error, because that's really what it is. It is what is unexplained by the model. All right, so, all right, let's, well, I guess I should go back. All right, if the treatment means are similar, this term will be small, all right? So, oops, I went too far. Okay, there we go. Factor variation. Sorry about that, guys. Factor variation is the sum of the square differences between each factor mean and the overall mean. So how much does A vary? How much does B vary? And what this is giving us is the amount of variation explained by the group alone. Okay, so this is the variation. If we had a column A, a column B, column C, and so forth, this would give us the variation across the columns, okay, if you want to think about it that way. If the treatment means are similar, so there's really not much variation, this term will be a small value, all right? The smallest possible value is 0, which says the treatment means are the same, all right? The percent of the variation explained by the factor is the adjusted sum of squares of the factor divided by the adjusted sum of squares of the total. All right, that sounds really terrible, right? No, not so much, because over here, let's go back into our additional options here. We checked estimates of the effect size and we checked eta squared. Eta squared, or the effect size, is the amount of variation in the model explained by group. All right, so this 0.503 is interpreted as a percent, so 50.3% of the variation in test score is explained by the group alone. All right, so in other words, let's take a look at our data. So all of these test scores vary, right? They're not all the same. I see a 50, I see a 74, I see a 98, and so forth. And 50% of the variation in all these numbers is explained solely by which group they're in. Okay, so in other words, group does a pretty good job explaining the variation that we see. All right. So again, you don't have to worry about calculating this quotient. You just need to make sure you've got your effect size, or eta squared, checked, and that's going to give you the percent of the total variation in test scores, or in the dependent variable explained by the factor. All right. So what's left? That was the residual. The unexplained variation is the sum of the squared differences between each observation and its factor mean. All right, so go back one more time. Let's go back over here and talk about what that means. All right, so let's just look at A. Okay, so we're just looking at these first 10 rows. And within A, these test scores vary. They're not all the same. So somebody scored a 50, somebody scored a 69. And what causes them to vary within A? And the answer is we don't know. That is the error, that is the uncertainty, that is the residual. Okay? All right, and go back. All right, so again, if we had our A column and our B column and so forth, the variation within each column is the error. All right, so how do we get to that percent? The percent of the variation unexplained is the adjusted sum of squares of the error divided by the adjusted sum of squares of the total. All right, do you have to do that? No, you don't. All right. How does 49.68% compare to 50.32%? Hopefully you see it as the complement to 100%. All right. So if you want the percent explained by the factor, you are going to check eta squared, or your effect size. You get the percent explained by the factor or the group here, 50.3%. The remaining percent to 100 is the percent explained by error. So 49.7% is explained by, or is unexplained, we would say. Okay, so that's how we get the 49.7%. It's just the difference between eta squared and 1. All right. You will also sometimes come across the term coefficient of determination, all right, which gives the percent variation in y explained by the model, all right, and it is the symbol r squared, all right, and r squared is often very important to us, especially when we get over to regression. Okay, so how well do all the x's do at explaining the differences in the y's? All right, so that's our coefficient of determination. All right, and I shouldn't say this week, I should say this lecture, matches the factor variation in percent. So we only have one factor. All right, so that eta squared that we are seeing, that 50.3%, that is our coefficient of determination. All right, we only have one x in the model. That one x is explaining 50.3% of the variation in y, and that matches our r squared. All right, and error, the error is always, forever and ever, always 1 minus r squared. Okay. You'll see in the next video when we have a couple of factors, we're going to have a couple of eta squareds or effect sizes. All right, but let's talk about what we want to do going forward when we do these ANOVAs, which is being able to compare them more at a deeper level. So we want to rerun our ANOVA, but this time under post hoc, we want to add the factor and check Bonferroni. All right. And so let's do that. So we want to rerun our ANOVA. We've got our group and we've got our score. All right. We've already done our assumption, so we want to go under post hoc tests. We want to move our group over. We can check effect size if we want. All right. We can get confidence intervals for those effect sizes. Now, under correction, you see Tukey, Sheffy, Bonferroni, and Holm. I'm teaching you Bonferroni, all right? We can leave it on, we'll go ahead and leave it on Tukey for the purpose of the lecture, that's fine. Let me briefly explain. Bonferroni and Tukey and Sheff, they're all doing different adjustments to the p-value to accommodate for that buildup of type 1 error that we just talked about. So we know if we just did independent t-test, we would get that buildup of type 1 error. We don't want that. So this correction being done is to give us a better p-value, okay? And under descriptive plots, move your group over to horizontal axis, all right? And you want to check display error bars. Okay, so let's briefly talk about what we have here. So you've seen this ANOVA table just a minute ago. And going forward, we want to do these post hoc tests. And so what this is this is giving us two sample t-tests, all right, with an adjusted or corrected p-value. So here A is compared to B, here A is compared to C, and A is compared to D, all right? I'm teaching you Bonferroni. So on the homework, on the quiz, on the exam, I want you to check Bonferroni. I'm going to be testing you on these p-values. I just wanted you to see Tukey, just so you know that they are relatively close. The Tukey p-values tend to be a little bit smaller. All right, Cohen's d, here's our effect sizes for our significant results. All right. And then here is our descriptive plot. So what we're seeing, these black circles, these black dots, are our sample averages, all right, for each group. And then our error bars here are giving us a 95% confidence interval around that sample mean. Remember, this black dot, the sample mean for A, is only coming from our sample of 10 firefighters. The question is, and what we're interested in, is what may be the population mean. And this 95% confidence interval is saying that with 95% confidence, we can say that A's population mean is somewhere in here, in between these bars, okay? And we're going to talk about how to interpret the post hoc tests as well as the descriptive plots here in just a minute, but I wanted you to be able to read them as we go through them. All right, we've checked our Bonferroni, and just to let you know, you can do what's called a Bonferroni correction by adjusting your alpha, and it's a kind of a by hand comparison. You just take your original alpha, like 0.05, and divide it by the number of two-way comparisons you're making. All right, so we would take our 0.05 here and divide it by 6, which is our number of paired comparisons, and we would get our new alpha. And so we would just compare our t-test results to that new alpha instead of 0.05. But in the software, when you check Bonferroni, it's actually doing a correction to your p-value, so you don't have to worry about that. You can just compare that p-value you see to your alpha of 0.05. All right, so we did our post hoc tests, and this again gives p-values for t-tests adjusted for the buildup of type 1 error. All right. And so here's a question. Do groups D and A significantly differ? All right. So we would have our null and alternative hypotheses here of mu D equal to and not equal to mu A. All right. And let's go over here to D and A. All right. So here's A and here's D. And we scroll over and we see a p-value of 0.035, so that should be 0.035. All right, and 0.035 is less than alpha. We reject the null hypothesis, and there is enough evidence to conclude groups D and A have significantly different means. All right, what if we wanted to interpret the effect size of that significant difference? Is the size of the difference between D and A very large? And the answer is, we would come right here to 1.125, And we know that an effect size greater than 1 is large to very large. So this is a large to very large effect size. All right. Is there a best group? So this is a question I'd love to ask. I'm certainly going to be asking it on the quiz this week. Is there a best group? How do we go about figuring out? And that's ultimately the question, right? If we're testing 4 different pedagogies, wouldn't we want to know what is the best so we can replicate that? All right, so we want to look at the interval plot of A, B, C, and D. All right, so we move under descriptive plots, we moved factor to the horizontal axis. All right, we checked our display and added the error bars. All right, so let's go over here and look at our plot again, right? So here's our plot, right? So if we did not know statistics, we would look at this plot and say, yep, C is definitely the best. But the question is, statistically, is C the best? Okay? And so we see right here, we see that C has the highest sample mean. The surrounding bars represent the 95% confidence interval for the population mean. But is C truly statistically the best? So we want to go back to our post hoc tests and notice that every pairing with C has a significant p-value. So let's go back to C. So here's AC, tiny p-value, significant. BC, significant p-value. CD, I am not getting a significant p-value because the reason is I think I ran this with Tukey. So actually C Tukey is significant, Bonferroni is not significant. So we actually should say that what we want to say here is that the pairing with D is not significant. All right, so there is not a best group. All right, so there is not a best group when we're using Bonferroni. All right. All right, so again, p-value here with C is less than 0.001. P-value with B and C less than 0.001. P-value with C and D is 0.059. All right, 0.059 is bigger than 5%. Not significant. All right, and one way you can see this, guys, is you notice here, let's look at our plot for a second. So do you notice how this error bar for C, the lower limit, overlaps with D? All right, so because they are overlapping means they are not significantly different. So that's just kind of another way you can see it, aside from just looking at p-values. All right, and we're getting there. All right, is there a worst group? All right, so again, we look at the interval plot. We see that group A has the lowest sample mean. All right, so let's go back over to group A. All right, we see group A has the lowest sample mean, but right away we see that group A's confidence interval overlaps with B and overlaps with D. All right, and so what that's saying is that if we look at the p-value for A and B, it is not significant. All right, we see here 1.000. And if we look at the p-value for A and D, also probably not significant. It is significant, barely 0.035. Wow, maybe I am not looking very well at it. All right, so, but because A and B are not significantly different, what that is saying is that there is not a worst. All right, and that's actually, oops, right here, that is 1.000 according to Bonferroni. And I apologize for that. I am so used to using Tukey. I use Tukey and my own analyses, but the people who were part of designing this class felt that Bonferroni was a better correction for you guys to learn than Tukey. So again, I apologize. But let's, final statement here. Since A is not significantly different from B, there is no worst group. All right. And again, I think that these lectures are important for your first exposure to what we're doing here, but I really feel like it's in the classwork when we do multiple examples where it's going to start to click.